Hi class. Today we're continuing our discussion on determinants. Yesterday I mentioned that we have three ways to compute the determinant of a matrix. The first way, which we discussed yesterday, was really the pivot formula. Namely, we carry out elimination on a matrix A to get to an upper triangular matrix U. Remember, matrices, when we talk about determinants, our matrices are square. So there may be a need for row exchanges in A, but eventually, if there are no row exchanges of A, what we have is that the determinant of A is equal to the determinant of U, and the determinant of U is just the product of the pivots. Okay. Now, the second formula that we're going to be talking about today is what's called the big formula, and you'll see why that's the case. And this one involves permutations. And the third way of computing determinants will be using the cofactors or cofactor formula. Now I'll have a video for each of these. Well, we already sort of did the pivot formula. I'll just review it shortly in this video. Then we'll talk about the big formula and then about the cofactor formula. I will be honest, we will only use this formula for a 2x2 matrix or a 3x3 matrix. I will explain it in the general case and why it is not efficient to use in bigger size matrices. However, it does give us information or insight into what the determinant is as a function of a matrix, how we compute it. And then we will focus a little bit more on the cofactor formula. Usually mathematical software will actually use the pivot formula, and if you know one way of solving a determinant, you know all ways. I mean, you can find the determinant. Whether you can use the second or the third way is a separate story. However, the cofactor formula is particularly useful when your matrix has a lot of zeros. It is also recursive. So I'll write that. This one is recursive, which means you can go from n to n minus 1 to n minus 2 and so on in a recursive way, and it is particularly convenient for finding formulas of certain special matrices. All right, let's remind ourselves on the pivot formula. As I said, goes with, so let's talk about the pivot formula. So our matrix may require pivot exchanges, but if row exchanges is what I meant to say. If A doesn't require row exchanges, then we know that A factors into L times U. Here the pivots are all ones, and here they don't have to be ones. If the matrix has a 0 along the diagonal, then you know that the determinant is 0. If it doesn't, you know that the determinant is not 0. Now, what is interesting is, let me take an example of a matrix U, which will have U1, 1, U1, 2, all the way to, well, maybe I'll have another one, U1, 3, and then U1N. Oh, sorry, this should be 2, 2, 3, 3, and N. These are the diagonal terms. We have something over here which is not necessarily 0, and we have 0 over here. So I really don't need to stress what those numbers are. They're not important. Now, an interesting observation for this matrix U is the diagonal terms are these u11, u22, u33. They come into play in the determinant, right? The determinant of u is the product u11, u22, u33, and so on all the way to unn. Now, you could look at this first matrix, right? This first pivot has to do with the determinant of that upper left corner 1 by 1 matrix. So let me call that matrix a capital U1. Okay, so I'll be calling that matrix like this, U11. It's just one matrix, a matrix with one entry. And then let me call U2, these capital U2, this matrix over here, the upper left 2 by 2 corner. So U11, U22. Okay, and one more example. I'll take this one, U3, U11, U22, U33. Ultimately, you understand if I take a U sub k, I mean the upper left k by k corner matrix. And now, the first pivot, U11, equals the determinant, or maybe I should write it the other way around. Okay, the determinant of U1 equals U11. The determinant of U2 equals U11 times U22. The determinant of U3 equals U11, U22, U33. So what do we have from here? And right, this continues all the way to the determinant of U being equal to the product of all determinants. Sorry, all pivots. All the way to UNN, right? The entire matrix from U11 all the way to UNN. The interesting thing is that now we have a way of expressing all the pivots through the determinants. You see, the first pivot is the determinant of the upper left 1 by 1 matrix. Now, what about U22? Well, I can express this as a determinant, and so it turns out that U22 is the determinant of U2 over the determinant of U1. That's the only thing that's new. Now, this part is the determinant of U2, which means that U33 equals the determinant of U3 over the determinant of U2. So again, what were U3 and U2? So here's U2, here's U3. So if I divide this determinant by this determinant, I'm going to find that pivot. And the process continues. The kth term, or the kth pivot, UKK, assuming it is somewhere inside, it is equal to the determinant of UK over the determinant of UK minus 1. So we actually can express the pivots through the determinants. Now, I gave you this example on a matrix U, which was already upper triangular, and its pivots were the elements, were just the diagonal terms. But the truth is, this actually works on any matrix. Like, let's say we take the matrix A here, 2, -1, -1, 2, -1, -1, 2, -1, -1, 2. This matrix, you can take your time and factor it. It factors into the following. 1, -1/2, 1, -2/3, 1, -3/4, 1 times, so this is L, And U is 2, -1, 3/2, -1, 4/3, -1, and 5/4, and that's it. So these are the pivots. Their product gives the determinant. You can immediately see that the determinant of A is simply 5. Now let's see what I did on the previous page, so these upper left corners. The point is that the first pivot over here only has to do with this matrix. All the elimination that happens is right here. So no wonder this 2 and that 2 are the same. Now this 3/2, you see, it only comes from this part. When you carry out elimination with that pivot underneath, this part is only affected by the first two components of the first row. No matter that these are zeros, that doesn't matter. If they were non-zero, then these terms would be affected. But this pivot really comes from elimination on this submatrix. Okay, so what we have is that also, if you have the determinant of this submatrix, we know that it is the product of the two pivots that the matrix has, and those pivots are exactly these ones. So just like in the previous case, if you have A1 to be the matrix with only the first upper left 1x1 submatrix, if you have A2 to be the upper left 2x2 matrix, A3 to be the upper left 3x3 matrix, 2, -1, -1, 2, -1, -1, 2, and then A4 to be the whole matrix, then it turns out the determinant of A1 is the first pivot, which is 2. The determinant of A2 is the product of the first two pivots, that's 2 times 3/2. The determinant of A3 is going to be the product of the first three pivots, which is 2 times 3/2 times 4/3, and that's it. And then the determinant of A, of course, will be the product of, or A4 if you like, the product of all the pivots, 2 times 3/2 times 4/3 times 5/4. And what you see is that each pivot can be expressed through the determinants. So the first pivot 2 is the determinant of A1. The second pivot 3/2, remember, this is determinant of A1. This is determinant of A2, and this is determinant A3. So 3/2 is the determinant of A2 over the determinant of A1. 4/3 is the determinant of A3 over the determinant of A2, and 5/4 is the determinant of A4 over the determinant of A3. Of course, I don't have to do this just on a particular example. This works for any matrix. The kth pivot will be the determinant of AK over the determinant of AK minus 1. And we don't need, from here you can actually see that we don't need row exchanges if all the upper left determinants are non-zero. So if you find an upper left determinant that's 0, for example, imagine you had a 0 here, then that determinant would be 0. That tells you that you need a row exchange. If you had a 0 here, that would mean that this row was a multiple of that row, so you would have a 0 there, so you would need a row exchange perhaps to bring this -1 into that pivot position. So these are some interesting observations about how the pivots relate to the determinant of a matrix. However, when the matrix is not triangular, so here the pivots are entries in the matrix. Here the pivots are not entries in the matrix, except for the very first one. But the other ones, they're not entries of the matrix A, and so the determinant isn't really related to its entries. Now, the big formula and the cofactor formula actually relate the matrix through to its entries. We'll see that in the next video.